Hello and welcome to Data Science for Everyone. In this video, I'll be talking about NumPy. Let's get started. In this video, we're going to build a strong foundation in NumPy. We'll start with the basics of creating and modifying arrays, since arrays are the core data structure in NumPy. We'll also cover how to convert between different types of arrays, how coercion works in NumPy, and how to get what we need from arrays through slicing. After that, we'll look at more advanced indexing techniques like masking, fancy indexing, and filtering, which unlock a lot of powerful ways to manipulate data. Once we have learned this, we'll dive into mathematical operations and how NumPy makes them efficient through vectorization. We'll then explore one of NumPy's most important features, summarizing and broadcasting. Finally, we'll tie everything together with a practical example of image processing. If you want a PDF document for all the codes and explanations, please leave a message in the comments below with your email ID and I can send that over to you. Also, if you haven't subscribed yet, please subscribe to my channel and like my videos if you are learning from them. With that, let's begin our NumPy journey. NumPy is a key library used in scientific work in Python. Libraries like pandas, scipy, and matplotlib depend on it. Even tools used in machine learning like TensorFlow and scikit-learn expect NumPy arrays as input. So what are these NumPy arrays and how we can start using them? At the center of NumPy is the NumPy array. It is structured in a way to store data in rows and columns. Arrays can have one or many dimensions, and each dimension can be as long as needed. Before using any features, we need to bring NumPy into our code by importing it. The standard way is to run import numpy as np. To create a simple one-dimensional array, take a regular Python list and pass it to the array method. The result is a NumPy array with one axis. To build a two-dimensional array, provide a list where each element is another list of equal length. This creates a grid-like structure with rows and columns. So why choose arrays instead of lists? Unlike Python lists that can hold mixed types of data, all values in a NumPy array must be of the same type. This restriction makes NumPy faster and memory efficient. Since the type is consistent, there is no need to check each element's type while processing. We don't always need to start with lists. NumPy can generate arrays directly using built-in functions like zeros, random, and arange. Let's look at a few examples. np.zeros makes an array filled with zeros. We have to tell the function the shape we want using a tuple like 4, 2 for 4 rows and 2 columns. This kind of array is useful when we want a placeholder for future data. np_random.random function generates an array with random decimal values between 0 and 1. We still pass in the shape using a tuple. It's called this way because it's a function inside NumPy's random module. np.arange creates an array of evenly spaced numbers. We can give it a starting point, an ending point, and an optional step. For example, going from 2 to 12 in steps of 2 gives 2, 4, 6, 8, 10. Notice that the endpoint is not included. This function is great for quickly generating sequences. As you work with NumPy, Python's built-in help function is a great resource. If you're not sure what a function like np.arange does, you can pass it to help without parentheses, and it will show a detailed documentation. The same information is available on official NumPy's website at numpy.org, but using help is often much quicker. Now that we have seen how to build arrays with 1 or 2 dimensions, let's explore one of NumPy's greatest features, its ability to work with data in multiple dimensions. Since working with higher dimensional data can get tricky, we'll also learn how to check and change the structure of arrays. Let's start with 3D arrays. To create 3D arrays, we can think of stacking several 2D arrays together. In NumPy, we can do this by creating a list of 2D arrays and then passing it to np.array. Visually, we can imagine it like a stack of spreadsheets, each with the same number of rows and columns. 4-dimensional arrays are harder to picture, but here's a simple way to think about them. Take a 2D grid and fill each cell with a 3D array. That's essentially what a 4D array looks like. Data organized across 4 axes instead of just 2 or 3. In programming and in Python documentation, you'll hear terms like vectors, matrices, and tensors. These come from math and describe arrays with different numbers of dimensions. A vector is a 1D array. In NumPy, 1D arrays don't distinguish between rows and columns because they have only one axis. If we want a horizontal or vertical layout, we can use a 2D array instead, so NumPy knows which axis we are referring to. Since 2D arrays have 2 dimensions, we do not call them vectors. In mathematical terms, 2D arrays is called a matrix. Arrays with 3 or more dimensions are referred to as tensors. These names help describe the structure of the data. Let's look at one of the most useful things about NumPy arrays, their attributes and methods. Attributes are built-in properties of an array, like its shape. Methods are actions we can perform directly on an array. For example, flatten and reshape are methods that allow us to adjust how an array is structured. The shape attribute tells us the structure of the array. It returns a tuple showing the size of each dimension. For instance, a shape of 2, 3 means the array has 2 rows and 3 columns. In NumPy, arrays can have more than 2 dimensions. So it's more accurate to refer to dimensions by their order instead of just calling them rows and columns. Let's take a look at this picture. The rows are called the first dimension and the columns are called the second dimension, and so on. Working with a single dimension is often easier than handling multiple dimensions. That's where flatten comes in. It takes all the elements of an array and puts them into a 1D array. The reshape method lets us change an array's shape without changing its data. For example, we can turn a 3x2 array into a 2x3 array. The only rule is that new shape must match the total number of elements. So a 6-element array cannot be reshaped into 3x3 because it would require 9 elements. Now let's take a look at what types of data can a NumPy array store. NumPy data tells us both the kind of data, like an integer or a string, and how many bits it uses. For example, np.int64 uses 64 bits, while np.int32 uses 32 bits. Choosing the right type can help reduce memory usage, especially if we don't need large numbers. A bit is the smallest unit of information in a computer. It can be either 0 or 1. A byte is made up of 8 bits. A 32-bit integer in NumPy can represent over 4 billion different values. That's because 2 raised to the power 32 is equal to 4.29 billion, and it can hold that many combinations of zeros and ones. A 32-bit integer can store values between roughly minus 2.1 billion to plus 2.1 billion. If we need to store larger numbers or smaller numbers than that, we'll need a 64-bit type like np.64. We can check the data type of NumPy array using the dtype attribute. If we create an array with floating point numbers, the default type will be float64. When we make an array, NumPy looks at values and chooses a data type automatically. If we use integers in our data, NumPy will usually go with 64-bit integers, and for decimals, it uses 64-bit floats. For strings, NumPy sets the type based on the longest string in the array. Here, the longest string is apples, and NumPy assigns the array U6, which is a Unicode string that can hold up to 6 characters. We don't have to let NumPy decide the type for us. When creating an array, we can set the type ourselves using the dtype keyword. This works with many NumPy functions like np.zeros, np.arange, and np.random.random. We can change the type of an array after it's made using the asType method. For example, if we have a Boolean array and want to turn it to zeros and ones, we can convert it to integer type. Note that the Boolean type in NumPy doesn't use a bit size because it only stores true or false. If we mix different types in a list when creating an array, NumPy will automatically convert them all to the same type. For example, if one value in an array is a string, everything becomes a string. This automatic conversion is called coercion. If we add a string to an array of numbers, the entire array becomes strings. Add a float to integers and everything turns into floats. Add an integer to booleans and we get all integers. This behavior helps NumPy save memory, but we should keep an eye on it. It can happen without warning. Now that we have learned how to create arrays, let's explore how to access and organize the data inside them. Indexing lets us access specific items in an array based on their position. In NumPy, counting starts at 0. Just like Python lists, we can use square brackets to index values. To get a single value from a 2D array, we need two indices, one for the row and one for the column. For instance, to access the value in the second row and fifth column, we can use index 1 for the row and 4 for the column. If we use just one index in a 2D array, NumPy assumes we want a row. For example, using index 0 returns the first row of the array. To get a specific column, leave the row index blank and use a colon instead. This tells NumPy to include all the rows, but only the column you want. For example, index all rows of the third column using colon, 2. Slicing lets us index a part of an array. We choose where to start and where to stop using a colon. In this example, we are indexing with values 1, 4. This will include the value at index 1, which is the second element. However, the element at the end of the index is not included. To slice a 2D array, we need to provide indexes for both rows and columns separated by a comma, as shown here. We can also add a step value to skip over items. For example, in 1D array, colon 2 selects every second row. In 2D arrays, we can add steps to both rows and column slices to skip values in both directions. The sort function arranges values in order. By default, it sorts along the last axis. In 2D arrays, that means sorting across rows. We'll see the largest value in each row move to the end. In 2D arrays, axis 0 moves along the rows and axis 1 moves across the columns. NumPy sorts along axis 1 by default in 2D arrays, so values in each row are sorted individually. To sort each column instead, we need to set axis equals to 0. This tells NumPy to sort down the rows instead of across them. Many NumPy functions use the axis keyword to control how operations are applied. So far, we have looked at selecting data based on position. But what if we want to pick values that meet specific criteria? That's where filtering comes in. In NumPy, there are two primary ways to filter data. One is by using masks and fancy filtering, and the other one is by using the np.where method. Each is useful depending on the context. We'll begin by looking at Boolean masks. To create a mask, we can check a condition for every item in the array. The result is another array, but this time it's filled with true or false values, depending on whether the condition is met. For example, if we have an array of numbers from 10 to 14 and we want only odd numbers, we can check which ones leave a remainder when divided by 2. Once we have the mask, we can use it to pull out the elements we want. This is known as fancy indexing. Think of it as filtering out everything where the condition is false and keeping only the ones that are true. So from our earlier example, only 11 and 13 would remain. Now let's work with a two-dimensional array. Suppose we have rows showing different teams, with the first column holding team names and the second showing scores. We want to find teams with scores above 50. First, we check which values in the second column are over 50. Next, we use that mask to pull team names from the first column, but only those whose scores met the condition. This lets us pull values from one column based on the logic applied to another. With fancy indexing, we get the values that meet our condition. With np.where, we get the positions of those values. This is handy when we want to use those positions later in our code. Let's take a look at np.where. In our team scores example, using np.where gives us the positions of teams whose scores are above 50. These come back as tuple of arrays, one for each dimension of the original data. Let's look at another example of np.where. Let's say we're working on a grid-based puzzle. We want to find out where all the blank tiles are, represented by zeros. We can use np.where to get all the positions of those zeros. The result is two arrays, one with the row positions and another with the column positions. That's because we need both to pinpoint each individual element in a 2D array. It's helpful to assign these to two separate variables so the results are easy to use. One powerful feature of np.where is replacing values conditionally. Let's say in our puzzle we want to turn all zeros into 5s. We tell np.where, if the value is 0, use a 5. If not, keep the original value. This lets us edit the data quickly while keeping the other values untouched. Now let's take a look at how to add and remove elements in a NumPy array. This is useful because real-world data usually needs some adjusting before it's ready to use. In NumPy, we can merge arrays along a chosen axis using np.concatenate method. This is handy when we are expanding our data, like adding more columns or rows. Let's say we have an array with lesson details and now we want to add 2 more rows for new lessons. We can combine both arrays using np.concatenate and pass them as a tuple. Since we are adding rows, we are working along axis 0, which is also the default, so we don't have to set it manually. If we want to add column names instead, such as grade levels, we can set the axis parameter to 1 in the np.concatenate call. This will stack the arrays side by side, adding new columns to each row. To remove elements, we can use np.delete. It takes 3 arguments: the array, the indices to remove, and the axis. For example, removing the second row in a 2D array means using index equals to 1 and setting axis to 0. To delete columns, use axis equals to 1 as demonstrated here. If we skip the axis argument, NumPy flattens the array before deleting. This often leads to unexpected results, so make sure you always specify the axis unless you want that flattened behavior. When we're exploring a dataset for the first time, it's natural to start with general questions. We want to get a feel for what kind of information is there. NumPy provides several built-in functions to help summarize data. Imagine we manage a fitness tracking app with 3 active users. We have stored their weekly step counts over 5 weeks in a NumPy array. Each row represents a different week, and each column corresponds a different user. Let's take a look at how we can analyze this data using NumPy. We'll begin with the sum method. This function adds together all the values in the array. For our data, the total number of steps taken by all the users over 5 weeks is 268,000. We can use the axis parameter to customize how to sum. When we set axis equals to 0, it sums each column individually. This gives us the total steps each user took across 5 weeks. Looks like user 2 was the most active. If we set axis equals to 1, the function adds across the columns instead. That gives us the total number of steps taken by all users each week. It helps us see which weeks had more overall activity. The min and max methods work like sum. With no axis set, they return the smallest and largest values in the entire array. In our dataset, the lowest step count in any week for any user is 12,000 and the highest is 22,000. We can also apply these functions across specific axes. The mean method calculates the average. Overall, each user has averaged around 18,000 steps per week. Using axis equals to 1, we can find the weekly average across all users. Most aggregation functions, including sum, min, max, and mean, have a keep dims option. When true, the output maintains its original dimensions, which can be helpful when combining arrays later. It's especially useful when we are doing further calculations or visualizations that require consistent shapes. The CumSum method shows the running total over time. If we set axis equals to 0, we get the total steps each user has taken up each week. This gives us a clear picture of progress over time. Visuals are powerful. For example, plotting a user's cumulative steps alongside average of all users can quickly show how their activity compares. These summaries make trends easier to understand at a glance. I have made detailed videos on how to use plotting libraries in Python such as matplotlib and seaborn. The links are in the video description. No NumPy tutorial is complete without talking about the power of vectorized operations. Let's dive in. When NumPy adds up the values in an array, it doesn't go through each one step by step. Instead, it adds them all at once. How does it manage to do that? Since every element in a NumPy array must be the same type, NumPy can hand off these operations to C, a much faster programming language. This is one of the reasons why NumPy runs so efficiently. Using C behind the scenes in this way is called vectorization. The cool part is, we don't have to do anything special to make it happen. NumPy does it automatically. For example, when we use the sum method on an array, NumPy calls C to do the work efficiently. In NumPy, computations are much simpler. To add 3 to an array, we just write array plus 3 and NumPy adds 3 to every item automatically. In math, we call a single value, like 3, a scalar, and NumPy supports scalar operations natively, thanks to its C integration. We can do the same for multiplication operations as well, as shown in the code. Vectorized operations also work when combining two arrays that are of the same shape. If we have two arrays of equal size, NumPy adds them element by element as shown in the code. The same rule applies for multiplication, subtraction, or division. NumPy handles this element-wise, so each pair of values in the same position are processed together. We can take regular Python functions and convert them into vectorized ones using np.where. Let's say we have an array of words and we want to check which ones have more than 4 letters. If we try just length, it won't work because it checks the array itself, not each element. By wrapping length with np.where, we can create a version that checks each word individually. Now we can get the correct result, a new array with true or false values for each word. Broadcasting allows operations between arrays of different shapes by automatically expanding the smaller one to match the larger. Previously, we discussed operations between arrays of equal shapes or with a scalar. But what happens when shapes differ? That's where broadcasting comes in. It lets us apply operations between arrays of different sizes by virtually expanding the smaller array to match the larger one. When we add a scalar to an array, that scalar is broadcast across the entire array. It's like the scalar is copied to match the shape of the array, but much more efficiently. As shown here, the number 5 is added to all the components of the array. Broadcasting only works when shapes of arrays are compatible. To check compatibility, compare the dimensions from left to right. Two dimensions are compatible if they are equal or if one of them is 1. This is checked for every pair of dimensions from right to left. If the rule fails for any dimension, broadcasting cannot occur and NumPy gives an error. Let's demonstrate with some examples. The first example adds two arrays and both arrays have the same shape, so the operation works. The second example adds a scalar to an array. A scalar has no shape attribute, so NumPy broadcasts it to match the array. The third example tries to add two arrays of different shapes. Since neither dimension is 1 or equal, NumPy raises an error. Imagine we have a 1D array with 5 elements and a 2D array with a shape of 2, 5. These shapes are compatible since the trailing dimensions are equal. Let's take a look at another example. Here we have two arrays. The first array, array 1, has shape of 2, 3, 2 rows and 3 columns. The second, array 2, is just an 1D array with 2 elements. At first, their shapes are not compatible for addition. So we reshape array 2 using the reshape method from NumPy. Now, array 2 has 2 rows and 1 column. NumPy's broadcasting rule say that a dimension of 1 can stretch to match the other array size in that dimension. So the single column in the reshaped array 2 can broadcast across 3 columns of array 1. The result is as if the reshaped array 2 were copied across all columns of array 1, but NumPy avoids making extra copies. It only computes the result on the fly. This efficiency is one of the key advantages of broadcasting, especially with large arrays. Broadcasting isn't limited to addition. We can also multiply, divide, or subtract as well. A row can be subtracted from each row in a matrix, and a column can multiply every column in a matrix the same way, as shown in these examples. In this last part of the video, we'll explore how to save arrays and load them later for use. We'll begin by looking at a special kind of 3D array, often used in machine learning with images, an RGB array. Each 1D array holds red, green, and blue values that together represent one pixel's color. For example, if a pixel's values are 22500, the pixel will appear red. A 2D array of these pixels forms a row, and stacking rows creates a full 3D RGB array. Let's load an RGB array stored in a .npy file and visualize it. While arrays can be saved as .csv or .text, the npy format is the fastest and most space efficient. To load it, we use Python's open function with the mode set to RB for reading in binary. We'll open a file named logo_rgb.npy and load it with np.load. The link to the logo file is in the description below. The result is stored in a variable called logo_array, and we'll use plot.imshow followed by plot.show to display it. To look at the individual color channels, red, green, and blue, we can slice the array along its third axis. This lets us isolate each color's values across all the pixels. We can visualize the individual RGB color channels as shown in the code. We can modify specific color values using np.where. Let's say we want to change every 255 in the array to 50. This will darken the bright white parts of the image. np.where allows us to set a condition and specify what values to use if the condition is true or false. To save the modified array, we can again use the open function, but this time with the mode wb for writing in binary. We can store the result in a new file, for example, dark_image.npy using np.save. If the file doesn't exist, it will be created. If it does, it will be overwritten. Now let's look at how to rearrange arrays by flipping their elements and changing their axis order. In machine learning, it's common to make more training data by slightly changing the data we already have. This is called augmentation. Imagine we have 1000 photos to train a model to tell if something is recyclable or not. We can double our dataset by flipping each photo and using both versions for training. That way, the model learns that the direction of the image doesn't matter when making its prediction. The np.flip function in NumPy reverses the order of items in an array. By default, it flips all the axes. Let's say we have an image as a 3D array with the logo data. If we flip it, the rows gets reversed, so what was at the bottom now appears at the top. The columns get flipped, moving left side pixels to the right. the color channels red, green and blue also get flipped. Red and blue swap places, but green stays in the same place since it is in the middle. Instead of flipping every axis, we can flip just one. For example, flipping only the first axis reverses the order of the rows in the image. If we want, we can flip the colors as well. Set the axis to 2, the third axis, and the red and blue values will swap while the rows and columns stay the same. We are not limited to flipping just one axis. To flip both rows and columns, but keeping the colors as they are, pass a tuple of axes like 0, 1 to np_flip. This flips the layout of the image without changing the color data. Now let's look at np.transpose, which doesn't reverse the content inside each axis. It swaps the axes themselves. If we have a 2D array, np.transpose will swap rows and columns. So the first row becomes the first column and vice versa. The data stays in the same order within each axis, but the layout changes. By default, np.transpose reverses the axis order. But we can also set a custom order using the axis argument. Let's say we have a 3D image array. We can switch rows and columns by changing the axis order from 0, 1, 2 to 1, 0, 2. This keeps the color data in the same place while flipping the rows and the columns. Make sure to use AXES keyword and not AXIS, and provide all the axes in the order you want them to appear. With that, we have come to an end of this lesson on NumPy. I'd like to request you to please subscribe to my channel and like my videos if you're learning from them. Thank you.